And then at this point, the intersecting point of this axis library, and the axis will give you the focal point. And the focal length is basically just counted from the center of this length to the intersecting point, and we call this focal length. But then when you have this in your calculation, you end up having a system focal length. How do I locate this distance? Well, if I send a parallel beam into the system, of course I'm going to intercept the axis library with the axis somewhere. But then this F prime system is counted from this point to here, to here, or to here, to here. This is a problem. Li Xiaolong, you get a point, right? When we have a distance, say 1 meter, I'm at the focal point, but my focal length, the focal length is 1 meter. Do I measure it 1 meter from this edge, or this edge, this point, or this point? That is a problem. Even though this is, well, I end up having a system focal length of 1 meter, but the edge of the length could be here. So somehow there's one plane need to be defined for the 1 meter distance, and that is something we'll be talking about when we introduce you the cardinal point. Okay, but now for now, just take it. This is the system focal length. That is the minus inverse of C. All right, and then the image condition B equal to 0 is also ugly, but it's easy to compute it in a computer. Okay, but this formula looks ugly, and then you can sort of reorganize it to something more similar to the length law of single length. Okay, but then you need to keep track of the sign of the variables. Okay, so this is the one side note I need to write here, so that you keep track of the sign, so that you can interpret the image well. Okay, and the important thing is that while the concept we extracted from the single length system are applicable to this two length system. Okay. Well, the first is that well, if you want to figure out the linear magnification of the image, well, under the image condition, we know the element A is the linear magnification. All right. So just go back. Under this B equal to 0, then A, this guy, is the linear magnification. So you can calculate it. Okay, and then we have done this calculation for the system focal length. We have this. Okay, and previously we have a simple extraction somewhere before that the ratio of the left and the ratio of the the right and left focal length is equal to the material ratio, right? So based on this relationship, you can deduce the left focal length from a known right focal length. So let's do it without going through another calculation. Then we figure out the left focal length by taking this ratio. Okay, and this comes from the -1/c calculation. Once you have this, then this can be obtained by using this, dividing this value. So this is sort of a convenient way, a fast track to get the results, right? And the angular magnification is based on the concept of a telescope. All right, so a telescope, by definition, is to have infinite system focal length on the right. and that corresponds to C equal to 0. Then you just copy the D from the last page to get your angular magnification. Okay, and this is interesting enough. If you compare the linear magnification and also angular magnification, and you can end up having a result that is quite useful and also quite conceptually interesting. That turned out that the angular magnification of an optical system is equal to proportional to the inverse of the linear magnification. Okay, so for example, for telescope, the linear magnification is quite small. Okay, the object, a moon, is huge, and then once you image it into your eyes, the moon is just like this big, very, very small. So the linear magnification is very small, but then the angular magnification can be huge. A small change on this angle gives you a big change at your output. And microscope is just the opposite. Okay, so microscope and telescope are conjugate optical systems, and this calculation tells you why, because the angular magnification is the inverse of the linear magnification for a system, for optical system. Okay, so this is basically the concept we sort of extracted from the single lens imaging system. But then we have another thing we learned before, like here. If we go back to the single lens system, we have when we set this d equal to 0, then we said that this x2 prime depend on x1 only. So we have this, right? x2 prime, this angle depends on the position of the x1 based on d equal to 0. But then another argument that is that the x2 prime is independent of x1 prime. Okay, we sort of use this statement to draw this cartoon, and then argue that the input plane is a focal plane, the left focal plane. But now we can also draw another cartoon based on this argument. Let's do it. That is the x2 prime independent of the x1 prime. What will happen if we do it? Well, for this one, x2 prime only depends on x1. Well, this is the two-lens system. If the output angle only depends on the position of this input ray, this means that this is a left focal plane. Okay, so this is another illustration based on d equal to 0. Then we say this is the left focal plane. Well, another thing is that when we set a equal to 0, then x2, the position of x2 only depends on the x1 prime. X1 prime, for example, this is a parallel beam. Okay, then you have x2 at 0. But if x1 has some angle, then you'll be having a point somewhere other than the 0 position. Okay, so this means that the output plane is the right focal plane if we have e equal to 0. Okay. So if we go back to think about what we learned today, basically we have A, B, C, D matrix. And then this allows you to sort of construct a system matrix through multiplication of individual A, B, C, D matrix. And then A, B, C, D, each element has a physical meaning for some specific optical phenomenon. Okay, so this is something that you learn today. An important thing is that, well, if we just, without looking into this, what did we learn? Well, we have B equal to 0 is the image condition, minus the inverse of C is the system focal length. On the B equal to 0, A is the linear magnification. Okay, and then we have C equal to 0, that is the telescope. Then D is the angular magnification. Right, so we learned about this A, B, C, D. And then we start to argue that if we set A equal to 0 or D equal to 0, then the location, the input and output are relevant to the left and right focal plane. So this is basically the summary of how we learned today so far. All right, is this clear? Any other question? All right. As always, you need to go back to review the material and think about that, okay? And do the homework. So this is the material I was supposed to give you last week, but I tried to do it very, very slowly so that you could more or less catch the material. But now, I need to start the second set of the lecture. And we have more materials. And you're going to see that the ABCD matrix is very powerful. Even it can be used to describe the laser cavity. So I will continue. The course schedule is sort of delayed. So the second part of the lecture is relevant to the sort of definition of the optical system based on the ABCD matrix, and then we're going to apply it to laser cavity. So we'll continue with this 1.4 and 1.5, section 1.4. Now we need to rigorously define a few input and output plane and also useful plane that characterize an optical system. Okay, I just touched this a little bit that when I get a system a focal length of 1 meter, it's not measured from the edge of the second length. It's measured from somewhere inside the optical system, and then so somehow, if the 1 meter the system focal length is measured from this point, somehow I need to give the system, this plane, a name, right? And in fact, this is called the second principal plane. Okay. For whatever optical system, there's an input plane and output plane that is well defined from your point of view. But then once we get a system focal length right here, then somehow inside this system there's a plane allow me to measure the 1 meter distance, and this is called the second principal plane. And for the first principal plane, that is relevant to the system focal length on the other side. Okay, so we'll have the second principal plane, and then previously I also told you that well, when you send the light ray through the center of the lens, the light ray does not bend. So somehow in the optical system, there exists some light ray that does not bend the angle at a certain point, and we call that nodal point. And so you start to realize that if we want to describe an optical system well, then we need to understand a few planes associated with the whole system. And we call those the point associated with those plane are called the nodal point. Okay. So now we want to define what we call cardinal point right here. Okay. Cardinal point. There are 6 cardinal points associated with an optical system, and you understood already there are two focal points, one to the right, one the other to the left. So the two focal points are already understood by you. Okay, but then the system focal length is between the focal point and some plane, and those planes are called the principal point, principal plane. Okay, and we need to identify where those planes are. Okay, if I know the focal point and also the focal length, then I can identify these two principal planes. Okay, and then there are two nodal points, and we talked about this already. If you send a light ray through the center of the lens, then the light ray does not bend, and that defines a nodal point. Okay, so we need to know how to calculate those important point and location of those important planes, so that we can describe the optical system properly. All right. So once we know all the cardinal points, and the optical system is specified. So this is important when you do the optical engineering. So between the two, the input and output plane, you have ABC matrix. So the first thing, when you talk about an optical system, you have an input plane and you have an output plane. That is crucial. Okay. Whenever you deal with the problem, the first point, the starting step is to define your input and output as an electrical engineer. Okay, so this is the common sense to you. So let's first define input and output. Then we'll be able to identify the focal point by sending a parallel beam into the system. Well, once you have this. Once you observe this focal point, then the focal length, in fact, is to move this ray backward to determine the focal length. But then you see that the focal length defined from this from this point to this point is not measured from this point to the edge of your output. So somehow you need to be able to calculate this. Okay. But then, to you, when you work with the optical system, this is understood to you. This is understood to you. What is relevant to you, in fact, is the distance between the focal point and the output plane. Right? If I stand here, and then I measure the focal point to be somewhere here. Well, to me, how do I describe this point? It's easiest, well, if this is the output plane of the system, it's easiest for me to describe distance from here to here. Not quite a distance between this focal point to some imaginary plane inside. So to me, it's more meaningful to know the distance between this point and this edge. Right? 比较long. Right? Intuitively, yes. Right? So this distance, in fact, is more important to me. I need to be able to know this T2. But this is just an imaginary plane, in the optical system, defining the distance between the length of the focal length. Okay. So so from this cartoon, in fact, you can quickly determine that this T2 is given by A minus A over C. By sending a parallel beam into the system, and then you extract this x2. That is the well, if you divide with this angle, okay, for parallaxal approximation, this tangent alpha is written into alpha, and this alpha basically is the x prime, x2 prime. So you continue to write it. This is x2 prime, But remember that this is a beam going down. This angle is negative, so you put the minus sign here. Okay, and then this once you take out this, you're going to see that this is going to be equal to A over C x1. Okay, and what x2 is equal to A x1, and then this is going to be equal to this, so you end up having this result describing this distance. Okay, and if you want to figure out the imaginary plane inside this, that gives you the right distance of your focal length. Then you need to figure out this S2. Okay, so from the geometry, you can further calculate this S2 given by T2 minus this value, and then you end up with this result. Okay. And then once you discover this S2, then you know exactly where the right principal plane is, or second principal plane. The principal plane defines the focal length of the system. Okay, between basically the distance between the focal point and the second principal plane is going to give you the system focal length. Okay, so this plane need to be well defined for your optical system. Otherwise, you don't know where are the two points giving you this system focal length. Well, by symmetry, you can also identify the first principal plane if you run the beam backward. Okay, so now the sixth current point, you can identify the focal point. Then you can identify the principal plane. Basically, you have you know the four cardinal point. Okay, so you do the beam, so the backward, then you can have the left focal length, and then you have the second principal plane. And at this the focal point, you define the left focal plane. Left focal point associated with the left focal plane, and then with the left focal length, you define the first principal plane. Okay, and then you can also associate. Well, if we specify this parallel beam going out, then you can also associate the location of those T1, S1 with the ABCD matrix. So this is the result from the calculation. Okay. So this is the result. You can identify S1. You can identify this T1 to define this principal plane. So go through this calculation. And then now you know how to calculate the four cardinal point, the two focal point, and two principal planes. Then it's time to talk about nodal point. Nodal point is that you send a light ray through the axis. This light ray does not change angle. Okay. For length, the nodal point is right at the center. For single length, the nodal point is right at the center of the length. But for optical system, the nodal point could be separated into two locations. Okay. And this is important when you want to draw an image. Okay. So you can sort of the nodal point is that the input output, the angle does not change. So you construct. Well, if you want to know this plane where they are, but you don't know where they are, so you give some variable s prime, and then set this as the input plane, set this as the output plane. So your optical system has this ABCD matrix. But then, if you want to identify this plane, then you add some distance right here. And then imagine that this is your right nodal plane. You have to add this distance so that the entrance angle of the input and output are the same. Okay, and then you end up having this rematches, and then you set a condition. Okay, you set a condition. Right on this axis, input and output are at 0 location. Okay, so this means that the M12 has to be equal to 0. This has to be equal to 0. So this and this is equal to 0. Okay, and the amplification, the angular amplification for these two libraries is equal to 1. Okay, so this means that the M22 has to be equal to 1 because the relationship between this and this is governed by this M22. Okay, so the first thing is that the M12 is equal to 0, so that you have the starting point on the axis and exit point right on the axis. So you have M12 equal to 0, and the unit amplification will require this M22 equal to 1, and then eventually you have this results to give you this distance. So once you have an optical system like this, then you can identify the nodal point, location of the nodal point to the edge of the optical system. Just like if I have a focal point, the distance from this focal point to the edge of the system is meaningful to me. Okay, the same thing. You finish this integration, and then you end up having the result for x and s prime. So you have the two nodal plane calculated from this. So today I sort of give you some flavor about how to use cardinal point to define an optical system. And once those cardinal points are defined, then it's easier for you to extract the sort of continue to do optical engineering and also optical design for your image system or for hardware applications. Okay, and we will continue this on Wednesday. But I very much want you to keep the schedule of the course materials so that you sort of don't get lost once we go deeper. So today I prepare a quiz for you to do quickly, hopefully quickly finish it. Okay. So, Eugene, do you have a quiz? Oh, okay. Okay. We have 3 questions for you to quickly finish.
Does someone have an extra pen, maybe?
Extra what? Extra pen?
Yeah.
Perhaps. Well, this is a good chance to know your classmate in the same class.
What's your name? Chinese or whatever. Chinese. Zhang Su Kai. Nice to meet you, Zhang Su Kai.
Did you learn your French?
Yeah, you.
What is the
Okay. Okay, bro. I see you.